So I think it's clear what makes this different from other kinematics problems that we've come across, and that is, in this instance, we're given the velocity, 20 meters per second, and initially I'm just going to get you to sketch the displacement graph that this um, particle moves at, with the intention of eventually coming up with a function, the displacement function. If you don't have the function, just draw the graph, and I'll give you, what's the time? Yeah, 30 seconds to do that. Go. Don't try and discover the function. Sketch the graph. You won't discover the function in 30 seconds. Draw a pair of axes, draw a line, done. Little bit easy. Okay. Oh, hang on. Yeah, okay. So, first things first, if you drew anything other than a straight line, then you're not right, because if it's got a constant velocity of 20 meters per second, the only function we know that has a constant rate is a linear graph, right? So I'm just going to zoom out now so that we can see that. Well, not see, I haven't drawn it yet. But I'm assuming most of you would have done something like this. I'm going to just do a rough draw here. Oops. Something like that. Anyone have anything different? If you had anything down here, like that, just remember that we can't really go backwards in time without a TARDIS, so should be like that. Two things are wrong with this graph. Number one, that could be a graph of anything. That could be a graph of y equals or s equals t. So in order to show context, what do we need to write in? Thanks, Ziggy. Just perfect. A point other than 0, 0. So we could go up to here and say just write, I don't know, 1 comma 20. That'd work, wouldn't it? So now our graph has context, even though I might not have drawn the graph steep enough or whatever else, and I'm not using graph paper, putting in a critical point, I call it, it's critical because it gives us scale or context. So do make sure that you put in a point. So that's now a whole graph, and I have to tell you now, that does reflect the problem. But what's the issue? We can figure that out. We can do it in a second. Just graphically. So if no one drew anything different, it's no wonder we can't see what the problem is. I'll draw another graph. How is this problem not reflecting the problem? How is this graph, sorry, not reflecting the problem? That's not what I asked, though. I didn't say how is this graph different. I said, how is this graph not reflecting the initial problem given? And the answer is, apart from I shouldn't have gone back below 0, sorry. Apart from not going below 0, the answer is it does reflect the problem. Doesn't it? It does. That is a particle moving with constant velocity of 20 meters per second. It just so happens that the initial starting position, I'm pretty sure it's a tautology, the initial position of the particle is what? Thank you, Elizabeth. 5 meters it has, doesn't it? So it has an initial position of 5. But this is still an appropriate graph, okay? So when you're given a velocity and you need to work out the displacement function, you can't do it unless you are given, excuse me, you are given the initial position or some other piece of information. It's usually the initial position, but it could be something else. Exactly. It could be any point, really. All I'm saying is that it's normally the initial position that's given to you, because it's normally, if you think about it from a scientific perspective, it's normally a piece of data that you have. You know, that it's got an initial velocity, it's got a velocity of 20 meters per second. So you can imagine it's a wind-up toy that's going to move at 20 meters per second. Well, it's a good wind-up toy, isn't it? So it's a wind-up toy that goes at 20 meters per second. You know where you're placing it. You're placing it 5 meters along the start line, or you know you're placing it at the origin at the start line, or whatever else. So you know where you're placing it. So that's usually a pretty common piece of information for a scientist to have. So let's put that a little bit of context in. Something like that. The particle's initial position is 5 meters away from the origin, is a fairly common way of writing it. Lily? Yeah, I'm not too sure how much context it would give you. I would say, without being given anything more than that, one would assume it's 5 meters in a positive direction, wouldn't you? I think it might say minus 5 meters away from the origin, or it would say 5 meters before the origin, something like that. Remembering that we're always talking about the particle moving in a straight line. So we're talking about it going up and down or left and right, sort of thing. So in a way, we get to choose what positive means. Okay, so I'm going to do the working out for this. And then we're going to determine exactly, we're going to look at some more complex problems. And I've probably taken a bit more space than I meant to, so I'm just going to create a new page here, which doesn't have the little crossies on it. So here's the working out. For S of t. So we start with V of t. And we know V of t is the same as S of t and S dash of t, sorry. So S dash of t is equal to 20. We know that V of t, or S dash of t, is the gradient of the function that's created. So S of t is equal to 20t. I haven't finished yet, but does that make sense what I've done? If V of t is 20, then the linear function must be 20t plus some constant c. Now c might end up being negative, so it might be 20t minus 5, for example, Lily, if it was in a backwards direction. But nevertheless, what we have here is an unknown value. Okay? We then substitute in the initial value is 5 meters. The initial position is 5 meters. So we can say at t equals 0, 5 S of t is equal to 20 multiplied by 0 plus c. I usually use a big C there, but I've made it a little c by accident. C is equal to 5.
If you're given the initial point, can you not just assume that if it's at 0?
You can, but that's great for linear. It's not always that easy. Do you know what I mean? And we'll look at an example where it's not that easy. So, yes, you can certainly shortcut some of this thinking, Lily. The danger is always assuming that the constant value will be 5 or whatever the initial value is. Well, it's not always true. Whereas this method I've got here, where you substitute in just a single line, and then you can let your logic take over, will set you up for any kind of problem. Okay, any kind of problem. I'm recording this, Sam, so you can go back at the start again and look at the wonder. So this value C is really just stands for a constant. So it just means some constant value.